about, you know, all these people that want to tell you something about decisions? Like, it's very important to make the right choice or to be decided, like to not think too much about a decision and to be quick about it. Well, this is my problem because I am really bad in making decisions. I don't know whether it's like just deciding to go out for dinner and there are just so many possibilities. Like, what should I even choose? So there comes a friend and they tell me, yeah, make it easier for you, we go to Italian place. So there are only 2 options left. So now you can raise your hand. Who would choose a pizza right now? Who would choose a pasta? And who didn't raise their hand because they were just too slow? I feel you, because this would be me. But there's hope for us, because as said before, we can use our experiments as a good scientist and just force the decision on the light, so it's not mine to do anymore. So, but we don't use just any sort of light. In fact, when we look really close into the light, then we see that it's made of some tiny, tiny pieces that we call single photons. So this is like the thing that's the light made of. We can say, yeah, it behaves like a particle. So now we have some particles to force our decision onto. But how are we going to do that? So this is how it looks in our lab, but in fact it's just a chip that contains some of these pipes that guide our photons to either the pasta path or the pizza path. So let's see what they will do. Because they actually behave like you sometimes, they are just particular individuals. Most of them now choose the pizza. But that's too easy, like that's boring, right? So let's make this a bit harder. We want them to suffer, just like I always do. So who of you would still choose the pizza if it had banana and curry powder? Come on, some curious people, yeah. Actually my photons, they're a little bit more curious and open, so let's just assume we have a 50-50 distribution now. And now they can really suffer with this decision, yeah. But what is it doing? Like it's actually enjoying itself, because as long as we don't look there, it pretends that it just doesn't decide, and it's living in a dreamland of a pasta pizza or pizza pasta. If we are looking though, then it has to decide, and we see, okay, it's in the pizza path right now. And as long as it doesn't look, it's like dancing the pizza pasta dance, and we can describe it with this quantum superposition. This rings a bell, right? Yeah, Schrödinger's cat. But today we don't want to talk about dead cats. So let's go back to the pizza pasta thing. If we cannot look at the photon, what can we actually do? So this question was also raised by Max Born some decades ago, and he was probably also troubled by decisions, and he came up with a rule that we call Born's rule. And he tells us, you cannot look at the photon, you cannot see this dreamland, like it's not real, this thing, but you can do something and measure something that's the square of this thing. So what you need to do is you need to connect these two paths that the photon can take, and then the photon that arrives here, it's so confused that it's interfering with itself, which means that this function that we always use to describe the photon, it's like a wave at the same time, that's a wave and particle, and it's interfering here. And so what we do is we try this out. We just take this thing and we square it. Why not, if Born tells us to do so? So the square of a pizza is still a pizza, obviously. Then a pasta is still a pasta. But then we also get this pizza pasta and a pasta pizza. Nice, right? And Born tells us that this, you can also measure this. It's not just like an equation. If you just send one photon after the other into this chip thing and count them in the end. But let's now send the same number of photons inside this chip, but not going through both of the paths at the same time, but only through one at a time. So let's start with the pizza path, which means we only have a pizza here in this function, so only a pizza squared. And then we take the other half of the photons, send them through the other path. What we get is a pasta, of course. And if we compare it now, we see, the sum here, it's different. So even if we take the same number of photons in the beginning, it makes a difference whether these two paths are open or if we just have one at a time. So this is like the magic of interference, and it's really, really nice. And we are thankful for Born for this, but there's some question. This is, why did we actually square this? Like, we don't know actually. So Born just said this in a footnote in one of his papers. And it's still not proven without some big mathematical assumptions why we square this thing. So let's try experimentally what would happen if we try something else than two paths, for example. Because the square means that we have just pairs of choices, let's take three things at the same time, which is a pizza, a pasta, and I was told something Bavarian would be nice, so here you go. And again, we do the same thing, we put them together, we let them interfere, and we now have this superposition of three at the same time. This should give us some interference here as well, right? Because we behave, we don't look there. Let's see. However, Born doesn't agree. He says, no, we cannot have a third order interference, that's how we call it. But we try anyways just to put it in the equation, use this thing, square it, we get a pizza, pasta, and then all these combinations of different things. So what we see is, it's missing the 3-course menu. I don't know where this is in the equation, but what we can do is we can try experimentally like before, and we can see if it's there. According to Born, it's 0, but we can at least try to check if it's really 0 or if it's just really small. Would tell us that we have a deviation here. So we did all of this, and we actually found a very small number, but we now try to be even more precise with the measurement. So let's see if we can make this number really exact. And we learned a lot on the way, right? So for you, we learned here decisions between 3 different paths. Then if we are indecisive, we get interference, which is cool. And also that Born's rule tells us a lot about the interference and what we can measure. And last but not least, it's not a problem if you're undecisive sometimes. The next time you are, just imagine you are a single photon and scientists like me are loving you.
Josefine Krause from MCQST. Thank you very much.